skip. But when does this
Video become educational.
The hypervelocity railgun parcel delivery system was developed for use in zero-atmosphere environments. It launches 10-kilogram parcels at a speed of 120 meters per second. The first test launch will be held on the moon at an angle of 20 degrees from the horizon. At the test site, acceleration due to gravity is 1.6 meters per second squared, and there is no air resistance. The investors made it very clear that if I did not get these calculations correct, I would be the package for the next test launch. So let's make sure we're right. With an initial launch angle of 20 degrees and a downward acceleration of 1.6 meters per second squared, find the expected launch velocity vector in 2 dimensions. In this question, we're given the initial launch angle, theta, as 20 degrees, and from earlier we know that the parcels are being launched at 120 meters per second. I'll write that down as v. If we stop to think for a second, we can recognize that this is giving us an angle and a magnitude, which is essentially polar coordinates. So I'll write that down as 120 and 20 degrees. Since we usually want to operate in the Cartesian coordinates x and y, we're going to need to convert from polar coordinates. And to do that, the equation is taking r, or in this case v, and multiplying it by the cosine of theta, or the sine of theta, depending on if we want the x or the y. Plugging these values in, we end up with a result of 112.763 on the x and 41.042 on the y. So the final answer can be written as v0, since we were finding the initial launch velocity. v0 is equal, it's also a vector, to 112.763 on the x and 41.042 on the y. Next, we're required to write a set of equations that would model the motion of the cannon shot in 2D. The equation for displacement can be written as d equals the initial velocity times time plus half of the acceleration times time squared. Since there isn't any air resistance, the acceleration zeroes out, and the displacement in the x is simply equal to the initial speed in the x times the time since launch. In the y direction, we do need to apply acceleration, and that's simply the gravity force, which is equal to negative 1.6 meters per second squared. Knowing this, we can say that the displacement in the y is equal to the initial y velocity times time minus 1.6 over 2 times time squared. To graph the motion, we just have to plug in values for time. So we'll start with the easy one. When time is 0, the position will also be 0. To make this easier to graph, we'll find the 2 remaining points of interest, being the apex of the flight and the landing point. To find the landing point, we need to find the time spent airborne. With a motion on a flat plane, y can only equal 0 when the motion is either started or finished. By setting y to 0, we can rearrange the formula to solve for t. This results in t equals 2 times the initial velocity in the y direction over gravity. Plugging the initial y velocity into the formula, we now know that the parcel was airborne for a total of 51.303 seconds. Plugging this into our equation for x displacement from earlier, this gives us a value of 5,725.024 meters. To get the apex, we have to find the point in time that the y velocity is 0. To do this, we can remodel the equation v equals v initial minus gt into the equation t equals v initial over g. Logically speaking, this value can often be estimated. Since acceleration is constant, and we're launching the parcel from the same height that it lands, the axis of symmetry will always be the midpoint between these two positions. Sure enough, if we plug in the values of the initial y velocity and gravity, we get a value of 25 0.651 seconds, which is roughly half of the total airborne time. Plugging this value into our equations from earlier, we get a point value of, roughly in the center, 2892.484 on the x, and 526.05 on the y. Now we can graph very horribly our parabola, and that is our flight path. If the angle were 70 degrees instead of 20, how would it affect the distance to the impact point? Let's start by creating a new initial launch velocity using the same polar conversion from before. So x is equal to 120 times the cosine of 70, and y is 120 times the sine of 70. Both of these are in degrees, of course. The resulting value is, on the x, 41.042, and on the y, 112.763. By using the angle 70 instead of 20 as our launch angle, we can see that the x and y values have swapped places. I believe this is because of the 90-degree offset between sine and cosine. When the angle d is 0, sine of d is 0 as well, and cosine of d is 1. Setting d to 90 instead shows that these values swap, and cosine of d becomes 0 while sine of d becomes 1. Going from 0 to 90 degrees shows that sine and cosine mirror themselves after the 45-degree mark. This means that for any launch angle, there exists a secondary launch angle with opposite x and y velocities. Setting aside floating point error, we can infer that for any given launch angle, there exists a secondary launch angle with a different time of flight that may be faster. With 70 degrees as the launch angle, most of the flight time is spent ascending, opposed to actually traveling horizontally. T ends up being a huge value in the order of 140.954 seconds, with a total distance of t of x 5,785.034 meters, which is slightly off of our initial target. Sadly, our postal workers aren't rocket scientists, and they won't be able to solve all of these equations we've been using on the job. Instead, we're going to create a formula which will generate an elevation angle for any distance on the moon. We'll start by deriving from the formula for finding a projectile's range, given r is equal to the initial speed squared times the sine of 2 theta over g, where we're trying to find theta. Rearranging this equation to solve for theta gives us the inverse sine of gravity, or 1.6 in this case, times the target distance divided by the initial speed squared, which is 120. All of that divided by 2. Because normal humans operate in degrees and not radians, we'll also be multiplying the numerator by 180 and the denominator by pi, so that we convert from the radians to the degrees. By creating a table in intervals of 1,000 meters, we can see that only certain values can be mapped. Which values cannot be mapped? Given the limitation of the launcher, anything
Over 9,000! What, 9,000?
Thanks, Vegeta. Any value over that number results in giving arcsine a value outside of the range -1 to 1, which is undefined. Looking closer at this equation, we can see that the maximum distance is directly correlated to both the gravity and the speed. Since gravity is constant, if we were to turbocharge the launcher to allow higher speeds, then we could write this equation to model what our maximum range is when given an initial velocity. Putting this into Desmos, it's easy to see how an increase in the initial speed results in an exponential increase in maximum possible distance. Next video, we'll be going over the implementation of these concepts from inside Unity. Thanks for watching.